All right, welcome to Generative AI Futures by ByteGoose AI. Today, we're going to get our hands dirty and dive deep into the world of custom AI voices. You know, if you're an AI researcher, you're probably tired of those generic robotic text-to-speech voices. Well, this explainer is definitely for you. We're going to walk through exactly how to fine-tune a really high-fidelity, super expressive voice model, and we'll be using the power of Unsloth to make it happen.
Okay, here's our game plan. First, we'll talk about why we're even doing this, going beyond those robotic voices. Then we'll pick our model and data, get that audio dataset prepped and ready, walk through the actual fine-tuning workflow step by step, and finally, save that custom voice you've created. Let's jump in. So let's talk about the big problem we're all trying to solve here. Most AI voices, well, they just lack soul, right? They get the words right, sure, but they totally miss the nuance, the unique pacing, the emotion, all the stuff that makes a voice feel genuinely human. And that's exactly where fine-tuning comes in. It's our answer.
Okay, this is a really important distinction to make. On one side, you've got zero-shot cloning. Think of it like a pretty good impressionist. You give it a short audio clip, and it approximates the tone, but that's about it. The delivery, the style, the pacing, that all still belongs to the original base model. Now, fine-tuning with LoRa, that's a whole different ballgame. It's more like method acting. The model doesn't just imitate, it genuinely learns the speaker's unique style. It captures their personality, all their little vocal quirks, and their true expression. We're talking high-fidelity realism here.
All right, on to step 2. To build a fantastic custom voice, you've got to start with the right building blocks. You know, your essential toolkit. This all comes down to picking the right base model, and just as importantly, the right data set to train it on.
So when you're picking your starting point, you've basically got two main paths you can go down. You could grab a base model like Sesame CSM. It's really powerful, for sure, but there's a catch. You have to feed it audio context just to keep the voice consistent, and that usually means you need more compute power. The other option is a pre-fine-tuned model like Orpheus TTS. The cool thing here is that it already has voice consistency and even emotional support baked right in, which means you're going to get better results faster right out of the box. Now this brings us to a really key piece of the puzzle for a lot of TTS systems, the vocoder. Think of it as the last step in the assembly line. It's what takes the model's abstract output and turns it into an actual audible sound wave. A lot of models need this as a completely separate step. But this is where Orpheus is a real game changer. It simplifies the whole process because it outputs audio tokens that can be decoded directly. No separate vocoder needed. It's basically an all-in-one system, which is awesome. Okay, for our walkthrough today, we're going to be using the Elise corpus. It's a fantastic little data set, about 3 hours of a single English speaker. Now, what's really cool is that there are two versions. You've got the base version, which is just clean audio and transcripts. But then there's the augmented version from Mr. Dragonfox, and this is where the magic is. It includes special emotion tags, things like laughs or sighs, written right into the text. And let me tell you, this is incredibly powerful for teaching a model not just what to say, but how to say it. All right, we've arrived at what is, without a doubt, the most critical part of this whole process. I can't stress this enough. Your final model will only ever be as good as the data you feed it. Meticulous, careful data preparation, that is the absolute key to getting a high-quality, believable voice at the end. Luckily, the process breaks down into 3 really clear steps. First up, get your audio and text pairs perfect. And I mean perfect. Every single audio clip needs a matching word-for-word accurate transcript, no exceptions. Second, you got to normalize those transcripts. Clean up any weird characters, and this is the important part, add in those special emotion tags if you want that expressive output. And finally, step 3, make sure all your audio files have the same consistent sampling rate. For the Orpheus model we're using, that magic number is 24 kilohertz. So let's look at exactly what this tagging looks like in practice. See this? I am very tired. That little size tag is embedded right there in the transcript. So when we're training, the model isn't just learning the words, "I am very tired," it's learning to connect the specific sound of a sigh in the audio with that special size token. And that right there is how it learns to generate not just words, but actual emotional expressions. And hey, if you want to use your own custom data set, the process is super straightforward. All you need to do is create a simple CSV file. Just 2 columns, one called file name for your audio files and one called text for the matching transcripts. The Hugging Face datasets library loves this format and will load it up for you no problem.
Okay, our data is prepped and ready to go. Now for the fun part. It's time to actually bring our custom voice to life. So let's dive into the code and walk through the fine-tuning workflow. You're going to see just how streamlined Unsloth makes all of this.
First things first, we need to load the model. We do this using Unsloth's special Fast Language Model class, which is built from the ground up to be super efficient for training. As you can see, we just specify the model name, we're using Orpheus here, and set a couple of key parameters for how it should be loaded. Now you might be looking at that code and wondering, wait, why are we setting load in 4-bit to false? And that is a fantastic question. This is a really crucial detail when you're working with text-to-speech. See, for massive language models, 4-bit quantization, or QLoRa, is an absolute lifesaver for memory. But voice models, they're way more sensitive to precision. So for what we're doing, training in 16-bit precision almost always gives you higher accuracy, and most importantly, much better, cleaner audio quality in your final voice. Step 2 is all about configuring the trainer. We use the standard training arguments class from the Transformers library for this. This is basically our control panel for the whole training run. It's where we set all the dials, stuff like the batch size, the learning rate, which optimizer to use, and exactly how long the training should run.
Let's zoom in on a few of the key arguments here. We're setting the batch size to 1, which is pretty standard for a single GPU setup to avoid issues. You'll also see we've set max steps to just 60. Now that's just for a quick demo run so you can see it work. For a real training run, you'd want to set num_train epos to 1 to go through the whole dataset. And check out the optimizer. We're using Atom W 8-bit. This is a really smart choice for saving memory because it quantizes the optimizer's state down to 8 bits, which can drastically reduce your GPU memory usage during training.
So, think about it. We've loaded our model, we've prepped our data, we've configured our trainer, everything is set up and ready to go. The big question is, how do we start the magic?
You're going to love this. It's this simple. One single command, trainer.train. That's it. That one line of code kicks off the entire training loop. It starts feeding our dataset to the model, and the process of adapting all those weights to learn our new voice begins. I mean, that's the real power of the amazing abstractions that libraries like Unsloth and Hugging Face give us.
Okay, once that training process finishes, there's just one last thing to do: save our work. We now have a model that has actually learned the unique signature of our target voice, and we need to make sure we save those new learnings so we can use them later.
And saving is as simple as calling the save pre-trained method on both the model and the tokenizer. Now remember, because we used LoRa for this, we're not saving the entire massive 3 billion parameter base model again. Nope, we are only saving the small, lightweight LoRa adapters. These are just the new weights that have captured our custom voice. It's just incredibly efficient.
So after all this, you might be asking, why go through the trouble of using Unsloth for this workflow? Well, here's the payoff. Thanks to its deep optimizations, you can fine-tune these exact models 1.5 times faster, while using about 50% less memory. That is a massive difference. It's what makes creating custom voices like this so much more accessible to everyone.
All right, let's wrap this up with the key takeaways. First, remember that true vocal expression is earned through fine-tuning. You can't get it from zero-shot cloning. Second, and this is the big one, data is destiny. High-quality, well-prepared audio is everything. Third, models like Orpheus make your life easier by getting rid of the need for a separate vocoder. And finally, using a tool like Unsloth is a no-brainer. It accelerates everything, letting you train faster with way less memory.
So there you have it. We've gone through the entire pipeline, from the why all the way to the practical code. You literally now have the blueprint to go out and create your own custom, high-fidelity AI voice that can express real personality. The only question left is a big one. Now that you can create any voice, what stories are you going to tell?